Before you leave today, you need to put your name, your Cornell card number, and your net ID on this piece of paper so that we can generate a list to activate you for the lab door. So if you don't get on this list today, there will be something like a 1-week delay before you have another chance. Sure. So last time I did a little bit of introduction to Verilog. I want to do a little more today. I also thought I should show you what the user interface looks like for the FPGA, the HPS system, the high performance system, because all you have is a console window. There's no graphic user interface. There's nothing but a 24 by 80 text window that you're going to do all your work in. So I wanted to talk a little bit about Linux commands, but not too much if most people have done this. Let's say who knows how to list files in Linux? Everybody? Everybody know how to change the permissions on a file? Do you know how to find the IP address? Okay, I don't need to say too much then. I'll say a little bit. I also yesterday decided I should write up a little something about Qsys, because every time I say the word, people's eyes get really big. And it is completely unfamiliar to most people, because it is a graphic language that has no other use except in Qsys 2. I did find a couple of videos on YouTube that explain how to connect modules, so I linked those up. But I'll talk a little bit about them, and particularly how they relate to these EBAB, the external Avalon Bus Master. But first I want to go back and check and pick up a little bit more on Verilog, particularly on blocking versus non-blocking assigns. So a blocking assign in Verilog might be some signal equals some other signal, where the simple equal sign means block. And this really doesn't mean much in an assigned statement, because every assigned statement, of course, happens in parallel with every other assigned statement. Where it gets a little trickier is where you have a combinatorial always block that is generating logic that has some depth to it. And first I'm going to state the rules, and then we'll try and motivate why the rules. And when you're modeling combinatorial logic, unclock logic, use an equal sign. If you're modeling sequential logic, in other words, clocked logic, you are highly advised to use a non-blocking assign. And unless you want to just shoot your foot off, never mix those in a block. Now, what's the difference? Well, there's a couple of examples. This is from MIT. It was some nice slides, so I used them. Let's look at non-blocking sequential logic first. Let's say we have this is the circuit we want to model, which is some sort of shift register. And we write it by saying always at pos edge clock begin in Q1, gets the value of in, Q2 gets the value of Q1, out gets the value of Q2. Non-blocking means that all of those assigns happen at the same instant. So there is no dependency between them. They all shift their right side into their left side. If you were to use non-blocking logic, non-blocking assigns, then what you're saying is set Q1 equal to in, set Q2 equal to Q1, then make out equal to Q2. And so in your brain you might think that is sequential assignments, but it's not, because there is no sequentiality in Verilog. Rather, you are synthesizing a circuit that has these dependencies, and so what you're synthesizing is this. You're clocking in the value of the input on the clock, and then Q1 just becomes the same as Q2, which is assigned to the out, which is not what you want if that's what you want to model. So when you want events to happen on the clock edge, in other words, if there is the keyword pause edge in the always, you will use non-blocking assigns. If you expect to model what you think you're modeling. Now, for combinatorial logic, let's say you have an always block where you say X is the logical AND of A and B, and then Y is X ORed with C. Probably what you have in mind, because you're used to thinking of a sequential system, probably what you have in mind is do this operation first, then do this. And so what you want to synthesize, because there's no clock here and therefore there's no sequentiality, is you want to build a combinatorial circuit that takes A and B and then combines them with C, and the output here appears effectively instantaneously. If you did this and expect that circuit, then you're doing something different. You're taking A and B on one clock cycle and C on the next clock cycle and combining them. Or something. So, just burn it into your brain. If you're doing combinatorial logic, use a blocking assign. If you're doing sequential logic, do a non-blocking assign. And of course, if you assign a signal in one always block, you cannot assign it anywhere else in the design, because that would be equivalent to connecting two voltage sources together. It's a bad idea. Something will break. Any questions on that? And I'll try and maintain that standard throughout all the examples. And you really need to do this in your code. So, can you all write a multiplexer 3 different ways in Verilog? You could use an if statement, which would instantiate a multiplexer in an always block. You could use a case statement in an always block, which would instantiate a multiplexer. Or you could use a conditional assign, which is combinatorial. All of these are combinatorial. That would do that. Is this familiar to you? Are you all okay? So I don't need to. I'll be happy to write them out if you want to see them. But if you don't, we'll move ahead. Anybody want to see them written out? Yeah. Okay. Now, where did the eraser go? So, for some reason, somebody thinks it's a good idea to hide the erasers behind the graphics. So, let's say we want a 2-to-1 mux. So we want to build a circuit that looks like this, where we have D1, D0. There's a select bit, so it's only a 1-bit selector, and then we have an output. One way to build this would be to say assign, we'll call this out, assign out to be equal to parentheses select question mark D1 colon D0, where this is the 1 input and this is the 0 output. So the select or the conditional says if this is true, if it evaluates to non-zero, take the first expression, otherwise take the second expression, and you can nest these to make n-way multiplexers. Second way would be to use an if statement. So you could say always at, and what I'm going to suggest is always use star, because that's the only thing that makes sense in synthesis. Always at star begin if select, well, let's be explicit, equal 1 tick binary 0, then out, oh, I shouldn't do that. I'm just going to say begin out equals D0 and else begin out equals D1 and we could also write this as a case statement, always at star begin case of select 1 tick binary 0. The obsessive programmer will always specify the bit length, because what is the default? If you just say 0, how many bits do you get? For any integer, in fact, 32. Case of 1 tick B0 output out equals D0. Case of binary 1 out equals D1. End case end. So 3 different ways of doing a mux. Which one you will use will depend a little bit on the complexity of the condition and how many mux options there are. For 2 mux options, this is pretty handy. For 3 or 4, it gets a little obscure to decode. If you have a regular condition where you have a series of bits that you're comparing, or a series of bits you're choosing on, a case is very nice. If, however, the mux depends upon some complicated logical condition which is hard to express except as, say, a logic or as a logic expression, then an if statement is going to be the obvious choice. So use whichever one gives you the most expressiveness and easiness of understanding, because they all synthesize to the same thing. So the rest of Verilog I'm going to do by example, by showing you some Verilog. In particular, we're going to start out by, in a very short while, looking at some bus masters, because that's a lot of what you're going to be writing this semester. But first, let's just do a little bit of Linux, then talk about Qsys. So I modified the Linux page to have a little more information on commands. 40 Linux commands that everybody should know. Newbie commands: cd, exit, kill. That being a process, not your partner. Probably the man is one of the most important, because it pulls up a man page which describes whatever command you want, often in quite verbose terms. And every single one of these commands, like ls, has 50 options. And so some of you will, what are your favorite flags for ls? Dash L. I like dash L, or sometimes A, or dash AL, if you want to see all the hidden files. And so because Linux is designed to be terse and customizable to a fault, you can redefine ls to be anything you like, including ls-al, if that's what you want to do. Remember that Linux is an offshoot of Unix. Unix was written the first time, does anybody know when? I think it was early 70s. 73? And there were only terminals, green screens, 80 columns, 24 lines. And so all interaction had to be through one dumb terminal. And nobody likes to type, so every command is made as short as possible, and therefore cryptic. And so the most used, there's kind of like a Huffman coding here, the most used commands are the shortest and hardest to remember, like ls, and then some of the others, shutdown, reboot, are a little bit longer. But you're going to need to use these, and you should probably paw through this a little bit, because your entire user interface is going to consist of initially a single terminal window. Because when you bring the system up from the image I gave you, it doesn't know anything about the network, and therefore you can't talk to it over the network. The only connection you have to it is through the serial port on the board, which you're going to map to a PuTTY terminal. And before you can get network running, you're going to have to do some basic housekeeping, assigning a MAC address and assigning an IP address by means of a config file, which means you're going to have to edit the config file in whatever editor is available on the system as shipped. And that editor is VI. So you're going to you really, really need to read a little bit about VI before tomorrow night if you've never used it. Everybody use VI?
Did you say that Nano was on here too?
You have to put Nano on there. It's not on there as it ships. You can get Nano on there, and interestingly, Nano gives you a mouse interface if you use the -M option on the command line. But the mouse only works if the mouse support process is running, and it appears to run by default. So you have a mouseable, kind of mouseable interface. It's weird. It doesn't act like every other cut and paste mouse you've ever seen, which was defined in the 80s by Apple. This is just strange. So you're going to want to play around a little bit with this. This TechSpot thing says how to switch directories, how to view directory contents. It's all very nice and graphical, and that's kind of nice. How to find the contents of a file, how to create a new file, how to rename, how to search. You're going to be logging in as root. You don't have to use sudo for anything. There's some network commands that I listed here, but you're going to want to use ifconfig to find out if you set the IP address correctly and the MAC address correctly. You're going to probably want to use ping to find out if you can talk to the router. You're going to want to then one of the first things you're going to want to do is an app update, I think, to once you get communication, to update the application loader to the current database. So any comments about any? Ishvan, you did some work with this, but you were using.
I haven't booted it yet.
You haven't booted it yet. Okay. So there's a new little page here called Qsys bus design. I suspect we're going to do a lot of Linux remedial work tomorrow night, and that's fine. And trying to get stuff booted up. Anybody have trouble writing a card? Anybody tried to write a card yet? All right.
The write protection switches on the cards you have flip really easily. I had to tape mine in the read-write position.
Oh, really? Well, I didn't buy the most expensive cards on Amazon. But that's interesting. Okay, so you might have to make sure that you could actually, that the read-write switch on the card is in the right position. I decided I should talk a little bit about Qsys and a little bit more. It's a bus design tool. We've talked about that. And Qsys hides a huge number of details about the bus from you. So I took this from an Altera manual. This is the old method where you'd take some processor and some interface and some other bus slaves, and then you write all of this stuff, the interfaces and the width adapters and some sort of ordering thing so that you know who's going to go first. And it packages that all up inside of some mystical chunk of Verilog which is generated for you. This has positives and it has negatives. It's easier to write, but you have no idea how it works. All right, and that doesn't matter until it doesn't work. But interfaces, address decoders, burst adapters, streaming to Avalon interfaces, arbiters, everything is all packaged up for you. And so you can do a fairly simple clean connect. If you have a data source, it's referred to as a bus master, you can connect it to a data sink, a bus slave connection, and it'll probably work. And that's pretty cool. The system knows enough. The signals on the bus are typed so that there's some error checking available. The types are clock, reset, Avalon signals, memory map signals. So these would be connections which are synchronization plus data. Just looks like a wire you drag. Avalon ST signals for streaming interface, and I haven't messed with those at all. I know very little about them. Hopefully by the end of the semester one of you will teach me. There's a tri-state interface for connecting to off-shift peripherals. Haven't messed with that at all. And a conduit. The conduit is the catch-all for everything else you couldn't figure out how to put onto Qsys. In particular, it is a way of allowing you to pull signals outside of the Qsys environment into Verilog so that you can connect to them. So when you specify an export, a conduit export, you're allowing those signals to be exposed onto the Verilog interface to your Qsys. And you'll be doing a lot of that. And I'll talk more about that. But to go back up for a moment, Qsys designs can also be hierarchical. You have this bus layout I've shown you a couple of times of a ton of wires going between modules. But the modules you see on that bus can actually be subsystems with their own bus structure. So you can hierarchically hide stuff. In the case of the VGA subsystem, if you look at the VGA subsystem definition at the top level of the university computer, which you probably should have done by now, you'll see that there's a dozen connections or so: character buffer, buffer slave, DMA control, DMA master, sysclock. Oh, and 3 outputs, 3 conduits that are pulled out to the export column because that is real hardware that has to be connected outside the FPGA. So this is pulled out and is exposed onto the module definition that Qsys generates. But for right now, we ask, what is that VGA subsystem? And the answer is, it is a mess, to use a technical term. So let's open that and take a look at it. That's what's inside that thing. And you can't read that, neither can I. But there's a VGA PLL, a Pixel DMA controller, a Pixel FIFO, a Pixel RGB resampler, a character buffer, an alpha blender, a dual clock FIFO, and then the actual state machine VGA controller, which generates the sync signals for the monitor. You mess with this at your peril. However, if at least one person in the class has decided they didn't want to use my version of the university computer because it was incompatible with version 16 of Quartus Prime. So they are using the version 16 university computer, which is fine, but the default VGA is set up for 320 by 240. And you will have to go in edit pieces of the video subsystem to convert it to 640 by 480. Took me about, I don't know, 3 or 4 hours to figure out how to do that. I think I documented it someplace. I'll try and find that. So the overall interaction is between masters and slaves on the network, which is actually a packet network. And Qsys master can generate packets, addresses, and bus requests. A Qsys slave responds to bus addresses, bus requests aimed at its address. And you can't predict what other activity is on that bus at any given time, or how many bus cycles or how many clock cycles it'll take, state machine cycles it'll take to actually figure out or to get a result back on the bus. So you must pay attention to the bus acknowledgments. The bus is non-deterministic in that sense, and so you have to pay attention to bus acknowledgement. And for pre-written modules like the video subsystem, handshaking is all taken care of for you. But when you write a bus master, you're going to have to watch the bus acknowledgments to make sure that data is there for you to read, or that your write actually accomplished, is actually done. So you have to act on a write and act on a read also. Any questions? So I showed you the video subsystem interface with 3 exported signals. If we go and look at the Verilog which is generated, there's going to be some module that is named something like the system, which was the name applied to the Qsys design by whoever laid this computer system out. And some signals that are exported, I simplified this for chatting, but there's a clock input, there's a reset input, there's a slider switch export, which goes to the vector of switches, which is called SW at the top level. You'll need that for this lab. There's an LED export, and on this board there are 9 red LEDs. So LEDR is a 9 vector. And in particular then, the VGA, those exported signals on Qsys appear in this module as I/O connections, which are going, so these are the signals that are exposed from Qsys, and these are the connections that are used to go from the top level module to the actual hardware. There's a horizontal sync, a V-sync, an RG and B signal, typical 5-wire VGA interface, plus blank and sync and a clock which runs the codec. So when you add a new module, when you add a bus master to Qsys, you're going to export the control signals for that bus master, and they're going to appear in the module. So I did kind of a cartoony version of this. So the top image here is the generic description from the EBAB manual. There's a switch fabric, which is stuff that's hidden from you. That's the Verilog that's generated by the Qsys interpreter. There's an external bus to Avalon Bridge, which is available on the module list that ships with the university IP. You can drag and drop that onto the bus. And then there's going to be the external peripheral that you write that does something like build a VGA screen or make an audio signal or do some filtering or whatever it is. But this is going to be the intellectual property that you generate going through the university IP, through the bus structure, off to some other module that's interesting, like audio output or video output. So the Avalon fabric is these connections over here. The bus master that you add is going to be just a module that exists, and it's going to take a clock and a reset. The reset had a couple of sources. The clock is the system clock, and the Avalon master goes off to wherever it has to go to write. In this case, it's going to go off to the on-chip memory that mediates the screen buffer, the VGA screen buffer. 1 byte per pixel, organized as 640 by 480. So the output here then is a pixel whose address is a RAM address and whose data is the color of the pixel. Right. The conduit then, the bus master external interface from the external interface conduit then is going to, when compiled, generate a interface in Verilog that looks something like this. These are the names generated. Bus master video is because I called it bus master video, and then external interface write data is generated because I called that external interface over there. And then these names are appended by the signal name internally. And I'm going to map these to then 7 different sources in my video module. Controlling the address, which controls the pixel address, a byte enable, which says, how much am I really writing? Am I writing a byte? Am I writing 16 bits? Or am I writing 32 bits? So this is really just a width enable. A separate read and write command. What am I asking for? Read or write. The ACK coming back and the write data, which in this case will be pixels, and the read data will be nothing here because I'm not reading anything. Then these signals, the signals here are going to be referenced in the module that you write to actually generate that address and generate the colors that you want. And for lab 1 you don't need to do this, but for lab 2 you do. Because in lab 2 the pixels that you write are going to be determined by the dynamics of the system that you were simulating in Verilog. You're going to be dynamically simulating a spring mass system, and the positions of the masses will be plotted as trajectories on the VGA by a bus master. Any questions? Oh yeah, and the actual controller is going to have at least 2 states. There could be a lot more if you have some complicated process going on. But there has to be at least 2 states in any bus master. There has to be one to generate the address plus the data, and then the second state to wait for the acknowledge. And then you can generate more addresses and more data, and then you wait for the acknowledge. And it's going to be 1 pixel per ACK that you're writing. You write a pixel, you wait for the ACK. You write another pixel, you wait for the ACK. You might be able to write several pixels at once. After all, these are byte-wide things. What if you wrote 32 bits at a time? Well, maybe that'd be 4 pixels. I haven't tried that. It should work. I haven't tried it. As I said, this video Busmaster doesn't do any read back. It's just blasting pixels out, which should be okay for the first lab or 2. If you want to read back a pixel, you should be able to read that bus. You should be able to read image memory, get back the value of the pixel, which could be nice for doing say a cursor overlay kind of correction. The audio bus master I wrote is a several state machine that reads the state of the audio interface. The audio interface is so slow. It's 48 kilohertz. It is synchronous. You have to give it data at exactly that average rate. You can give it bursty data because it has a 128 word FIFO on the input and output. But you have to read it often enough to keep those FIFOs non-empty. It produces data, it has an ADC input. It produces data that appears in a FIFO that you can read. So that if you're going to read the audio, do some digital work on it, let's say you want to do speech recognition, or you want to make a speech vocoder, so you can do pitch shifting, you would read that channel at 48 kilohertz average, but it would be bursty, do the calculation, and then put out the signal, audio signal again onto the audio codec. So you have to be able to do a read-write. You have to be able to read the FIFO state, read the state of the left and right channel, the voltage level of the left and right channel, read the FIFO state for the right, and then write the left and right channel. And the way the FIFOs work, the left and right channels are always in sync. You can't play a new voltage until there's a FIFO entry in both channels, so I'm not sure why they have a FIFO counter for each channel separately. But they do. So oh yes, there's one more detail. When you put the EB-AB onto the bus, onto the Qsys bus, you do have to specify 2 parameters in a dialog box. How many bytes of address range can it address, and the data width. That's easy. So there's a couple of video examples which you may want to look at. The second one, the introduction to Qsys, was useful, but it's not specific to HPS. It's actually using the old NIOS 2 microcontroller. Then there's a HPS specific video, which I thought was pretty good. It's a little long. It's like 20 or 30 minutes long. But it shows you how to drag and drop connections and what it means to set up the bus. You might want to look at that. So the way I got some feel for Qsys was to start with the university computer, which has every possible module on it. And it's got switches, it's got LEDs, it's got push buttons, it's got video in. Oh, you can hook a television camera to this board. It's got video in, it's got video out, it's got audio in, audio out, it's got SD card drivers, it's got all kinds of stuff. On the left-hand side of Qsys, there's a box that says, don't use this module. You click it, it leaves all the connections there, so you don't have to reconnect it, it just disables it. And what you should do is just go down, click, 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 turn off everything on that bus, except maybe the LEDs, and then write a program on the HPS that talks to the LEDs and blinks the LEDs once a second. And then when you got that going, you could delete that module and rewrite it if you wanted to. It's pretty easy. All it is a parallel I/O port. The LED module is a generic PIO, which is draggable off of the menu. It's a generic PIO port that's been renamed LEDs and connected to the LED bus. But you could easily do that in Verilog. So you say, wait a minute, where is it getting the clock from? Well, it's getting clock from whatever clock source the HPS is using. Where is it getting reset? Wherever the reset is for the HPS. And where is the data coming from? Well, you get to choose that. But probably, since you can't see above about 100 hertz blinking rate, you may as well hook that to the lightweight bus, which is rather slow. And that is, in fact, the default connection. The lightweight bus is a bus master. You drag that connection down and connect it to the LED module, and you've got communication between the HPS and the LEDs. So, play around. Get rid of every module except, don't save it. Get rid of every module except the LEDs. Disconnect it. See what happens. Disconnect the slave. Connect it to a different slave. Connect it to the high performance bus and remap it. You play around a little bit, because that's the only way you figure out what the limitations are on this. I spent a lot of time playing around with this during the summer and all spring. I have the feeling I've learned maybe 10% of it. I'm not sure, maybe less. Any questions on this? So there should have been a piece of paper that came around in which I have everybody's name. Do I have everybody's name now? If your name isn't on the paper, you won't have access to the lab. So see most of you tomorrow night.